notice I didn't number them. So let's go down the first column. Okay, so we're on the back of page 4. Let's go down the first column. Okay, who will volunteer your answers to those 3 problems in the first column? Charlie, thank you.
I said 1/2, 2, and I said the terminal array of data.
That's what I said. I'm not saying you're right, although Charlie's usually right. But anybody have a question about any of those 3? Okay, you all good about that? All right, go do the second column then. On that same page. Annie, thank you.
4 1/3 A.
Bingo. 4 1/3 and A. Are there any of those we need to talk about?
Why would the second one be 1/3?
Why would it be 1/3? Well, let's look at the equation and see. What is the period of the tangent supposed to be? Pi. Okay, so let's look at this graph, and what is our period? Now, the period you can calculate either asymptote to asymptote, which they're implied here, not actually drawn, or dot to dot. So I got a dot at the origin. Where's the next dot? 3 pi. The next x-intercept is at 3 pi, which means my period is 3 pi, and it's supposed to be pi. So whatever the b is in the equation, it divided pi and gave me 3 pi. Okay, do you see what's going to happen? So now when I multiply and divide, it turns out to be 1/3. So tangents work exactly the same as sine and cosine, except the standard period is only pi, not 2 pi. All right, anything else on that page? All right, next page, that is the front of page 5. First column, who has answers to the first column? Parker? So Rose rather fast. So we'll say negative 0.372. So 1, negative root 3, and negative 0.372. How did Parker get negative 0.372? He remembers that tangent is y over x. So here's the y. Okay, any question about those? Good job. All right, and then the last column on the front of page 5. Last column. What did we come up with there? I'm going to call on someone. Thank you this time.
Negative 1.268, 0, and then 1.49.
Yep, negative 0.268, 0, and 1.439. You good with that? All right, and then the back of page 5. Some of these questions were quite interesting. What did you think? Who got an answer on the back of page 5 for the first column? Someone new who can give us the answer choices. Yep, Celeste?
Negative 1.154, and then D would be.
And then you said, okay, let me check that first one. I did not get negative 1.154, but I could have typed that in wrong.
Oh, it's 1.169.
There we go, that sounds better. Negative 1.169. And then you said that multiple choices were both D as in boy?
The first one was D.
Oh, the first one was D, and the second one was B? All right, I happen to agree with that. Anybody have a question? Did you notice that the tangent, half of the tangent is concave down, and the other half is concave up, right? Is that true of the sine and cosine? Half of the sine is concave down, and half of the sine is concave up. All right, last column. Last column, what'd you come up with? Someone new, call on someone. Like Evan, what did you get for that last column? D, C, and D. That's what I got. Any question? D, C, and D. Did you notice that the tangent is always increasing? Isn't always going up? Yeah. So it's always increasing, but sometimes it's concave down and sometimes it's concave up. Okay, now you might need to get out another sheet of paper because we're going to practice graphing these on our own. Some of these questions involve the sketches, so I'm sure you were drawing little sketches off to the side. But let's actually draw.
That works.
We're gonna sketch 3 of these, so again, you might need a piece of notebook paper. Oops, sorry about that. All right, so here we go. First thing we notice about this is that we have no shifts, so no translations, and no dilations except for this one, right? That's going to be a horizontal dilation, and what's it going to do to the picture? Divide by 3. So, normal tangent, asymptotes at negative pi over 2 and positive pi over 2. That is the normal. But what am I doing here? I'm dividing by 3. So where are these going to be? They're not going to be at negative a half and a half. They're going to be at negative 6 and 6. Another way you can figure that out is you know that the period will be pi divided by 3. That means asymptote to asymptote is a third. So if your dot is in the middle, if asymptote to asymptote is a third, then isn't middle to asymptote going to be a sixth each way? So it's another way you can figure that out. And then our tangent has a negative in front of it, which means it has been turned upside down. When you sketch it, it's hard. You're probably using notebook paper or something, and it's hard to do this. But if you did have graph paper, remember what I said in the video, halfway in between, you should be up 1 and down 1. So in this case, you don't have to label these points, but when you are sketching it, to get the curvature right, halfway in between, we're just up 1 and down 1. So if I had a graph paper, I could actually plot that point, and then I would have my curvature just right. Okay, is that all right with everybody? That was kind of easy. Let's look at this one. notice is that I always call it a dot, we should call it like an x-intercept. My x-intercept for a normal tangent is at the origin. Well, that x-intercept has been moved. That x-intercept is now over here at pi over 3. Because we have a phase shift to the right. And your phase shift moves your origin. The origin is right there, dot. That dot got shifted over to pi over 3. Everybody okay with that? Now, on either side, I'm going to have an asymptote. Normally, those asymptotes would be pi apart. But now, the asymptotes are actually going to be 2 pi apart. Is that all right with everybody? Which means, if I'm the dot, and my asymptotes are 2 pi apart, how far am I going each way? Pi, thank you. So I'm gonna go pi, so that's a third, so there's 1, 2, 3 thirds here. So this is negative 2 pi over 3. And this would be 4 pi over 3. And then halfway in between, I'm up 1 and down 1. So there I am. Is there anything about that you're not sure about? Tell me,
Sorry,
what is happening back
sorry.
there? Okay, let's focus, okay? We are, after all, talking about the tangent. All right, everybody good with that? One more to sketch. Let's try this one. Wow, okay, there's a lot going on here. So, we got a new midline. We got a vertical translation. So we've been picked up 1 unit. So now my dots, my x-intercepts, will be on that line now. And the first one is going to be at negative 2 pi. How far apart are my asymptotes going to be? There's an asymptote on either side of that dot. How far apart will they be? 5 pi? Why are they going to be 5 pi apart? Because that's a period, and the period is pi divided by a fifth. Right? Now, if they're 5 pi apart, then how far are they from that dot right there? 2.5 pi. So that's 2 pi right there. So 2.5 pi would be like right here. So what, pi over 2? And then 2.5 pi this way is going to be at negative 9/2. Or negative 4.5. You can use decimals or fractions. Now, I know this is my point of inflection, so here I am concave down, I'm gonna hit that, and I'm gonna become concave up. To get my curvature, I'm gonna pay attention to that number right there though. What does that tell me? That tells me that halfway in between, I'm not up 1, I'm actually gonna be up 2. So this is gonna be steeper than the other one. This is gonna be steeper than the other ones. And then here, I go down 2. So it's gonna look like that. Okay, so a normal one would have been like this. See the difference? It's straightened out because it got times by 2, so that's stretched. You good? All right, let's take a look now at page 7. 3.8 will be due on Wednesday. And we're gonna start 3.9. Good. So let's look at the notes on page 3.9. And first of all, today, as you can see in the headline, we're talking about inverse functions. The inverse of the sine, the inverse of the tangent, the inverse of the cosine. The notation for inverse functions, you're used to one of them. This is what's on your calculator. That's the inverse sine notation. And the way we would read this, let's put a number here, like 1/2. This literally says to me, the angle whose sine is 1/2. There is another notation used for the same thing, and it's this. These two notations mean exactly the same thing. They are both, I know it's tempting, and I do it myself all the time. I read this inverse sine, but it's really arc sine. These are both read as arc sine. And they mean the angle whose sine is 1/2. So what would the answer to that question be? The angle whose sine is 1/2 is? Ay. Pi over 6, thank you, pi over 6. Now, something should be popping into your head right now. Does anybody have a question when I say the answer to these is pi over 6? Does anybody have a concern? Caitlin?
Shouldn't there be 2 answers?
Oh, couldn't there be 2? And actually, couldn't there be a lot more than 2 if we're allowed to go around more than one time? But even in, you're right, in one revolution of the unit circle, there's 2 places where the sine is 1/2, right? And that makes sense if you think about your sine curve. Here's your sine curve. This is 1. Here's 1/2. Aren't there 2 places right there? This is not good, because what you're telling me is that on the sine curve, at pi over 6, I get 1/2, and at 5 pi over 6, I get 1/2. That's true. But now I want to inverse those. What happens to those ordered pairs when I inverse them? Now I have 2 ordered pairs with the same x. Is that allowed? No. So, some really smart guys a long time ago said the only way we can prevent this, the inverse of the trigonometric functions is not a function. Sine is clearly a function. Would you agree with that? Sine is a function. But its inverse is not a function. It would look like this. So they said the only way we can prevent that is if we restrict the part of the sine curve that we look at. So instead of drawing the whole curve, what if I only drew the blue part? Would the inverse of the blue part be a function? Yeah, because it passes the horizontal line test. So whenever I see either this notation or my arc sine notation, I am limited to negative pi over 2 to pi over 2. So in other words, when you answer a question using either one of these, whatever you write down has to fall in that interval. These are called the principal values. Remember, you get no reference sheet, so you will need to memorize that the principal values of the inverse sine are from negative pi over 2 to pi over 2. So on your unit circle, you'll only look at the right side for inverse sine. Now, the good news is, same is true of the inverse tangent. And that makes sense, because if you think about what your tangent curve looks like, doesn't it go from negative pi over 2 to pi over 2? Yeah, that one works out perfectly. So inverse sine, inverse tangent have exactly the same principal values. Negative 90 to positive 90, negative pi over 2 to positive pi over 2, quadrants 4 and 1. Right here, this part of the circle. Now, what about cosine? Boy, it would be great if cosine would have the same principal values. Well, let's look at the cosine. We are used to graphing the cosine curve like this, but if we go back to pi over 2, here it is. This is that part of the cosine. Does it pass the horizontal line test? So it is going to have different principal values. Instead of looking from negative pi over 2 to pi over 2, we're going to look from 0 to pi. That's the part of the cosine curve. Yeah? So the inverse cosine has principal values in the top half of the circle. So from 0 to pi. Charlie?
So for sine, it's all positive y values, and for cosine, it's all positive x values. Is that it?
No. The outputs, the angles for the inverse cosine will all be positive
Yeah.
angles.
Okay.
But the inputs can be negative. So, for example, if I said, what's the angle whose cosine is negative half,
Oh, okay. I see.
then that puts me over here in quadrant 2. So the inputs can be positive or negative. Notice you have a positive and a negative quadrant for each of them.
Okay.
The outputs for the cosine will all be positive, but the outputs for the tan and sine, some will be negative because you're at negative angles here.
Okay. Gotcha.
Okay? All right, so let's look at a couple of problems. Wait, what's example 1? All right, example 2, here we go. Evaluate the following expressions. So think about the part of the unit circle that you are allowed to look at. And you want to find the angle whose cosine is negative root 2 over 2. out what part of the circle am I allowed to look at. For inverse cosine, I'm looking at the top half of my given circle. If the cosine is a negative number, aren't I looking over here? And if the cosine is √2 over 2, what kind of angle is that? Pi over 4? But it's over here, so which one is that? So the answer to the question is pi over 4. You have done this kind of problem before, but you had 2 answers. Now we only have 1. This notation, these notations indicate 1 answer. All right, how about B? The angle whose sine, so this is an inverse sine, so I'm looking over here, and it's negative, so I'm looking down here. Sine is the y. So what size angle is that? What is that, pi? It's not a pi over 4. That is a pi over 3. So be careful. Don't say pi over 3. You gotta say negative pi over 3. Why do I have to say negative pi over 3? Because all of my answers have to be between negative pi over 2 and pi over 2. Those are the rules. Is this in exactly the same place as 5 pi over 3? Yep, it surely is. But I can't answer 5 pi over 3 because this is how I have to answer. The angle whose tangent is √3. This half, tangent is √3. What size angle has a tangent of √3? Wouldn't it be that same one? So what is the answer to C? Pi over 3. So C is pi over 3. Celeste?
Well, why for B does it have to be pi over 3 and 5 pi over 3?
Because you have to be in this interval. These are called the principal values. Every answer to that question has to be in this interval. Because remember, when we looked at our graphs, Celeste, we said we were gonna look from here to here. Now, all that is repeated over here, but that's not where the part of the curve we're looking at. We're looking at this part. So whatever you write down as your answer has to be between negative pi over 2 and positive pi over 2. Okay? I know that's confusing, but the reason that is because your calculator is a function machine, and it can only operate with functions. And the inverse function, the inverse trig things are not functions. So they have to set rules, and that's the way they set up the rules. So tan and sine, cosine. Okay. All right, I'm going to stop there because our period's almost over. So we'll probably wrap this up tomorrow, this particular section, and then we will the next time have a little quiz, couple of problems, one tangent and one inverse. So yeah, homework due on Wednesday. Have a great day, everyone.